So I'm going to help you out from the beginning here for a little bit. And then I'm going to try and let you pause the video and try and get as far as you possibly can on your own. So first of all, we would like to be able to label things that are unknown to us. Point C is unknown to us. We don't know what the point is, but we do know one thing, and we know that it's on the x-axis. We know we must leave from the shore to get to the water. And so since we have the x-axis here representing that shore, we know that C must be on that x-axis. So we do actually know our y value here, that it must be 0. Besides that, we don't know what the x value is, so we just put x for the x value. It's our unknown, right? Also, now take a second and try and figure out, what am I trying to minimize? I'm trying to minimize time as quickly as possible. So I need to have an equation that first, just an idea of the equation that represents the total time it takes for me to get to the swimmer. So breaking it up into parts and into pieces to bring it back into a formula is going to be key here. So we have two parts here. We have a part where they are running, and then we have a part where they are swimming. Each one of those is going to be its own individual situation, but we know that combining them together will give us the entire time. So time total must be equal to the time along the land plus the time along the sea. And so our goal then here is to put in an expression that represents time on land and put in an expression that represents time on sea. I would also like to give you one more hint before I let you go. Remember that speed equals distance over time, and that relationship can be changed to represent whatever you want it to represent. Oh, whoops. D equals S times T. There we go. Okay, those are all the hints that I'm going to give you. I would like for you to pause the video here and see how far you can get on your own. All right, so we know that we want to represent time on land and also time on sea. So I'm going to deal with each of them individually. First of all, the time that it's going to take for me to run on land is going to be the distance divided by the speed that I have on land. So I know that, okay, I need to represent the distance of this part of the land as well as the speed. And we've been given the speed, and we know that the distance must just be that x distance. It looks to be like 200 something, but we don't know that for sure. It could be 100 something. This is just an example. So we need to represent that distance using this variable right here. So the distance will be x in this case, divided by the speed. So this is where some things might get a little tricky. The speed, remember, is distance over time. And so if it says, hey, on land, 3.5 minutes per kilometer. So our speed for that guy is going to be distance, 1 kilometer, over time, which is 3.5 minutes. Okay, so that's going to be our speed that goes in the denominator, except for we need to keep in mind one thing, that these values are all given to us in meters. So we need to make sure that our speed is also being represented by meters. So I just need to convert this really quickly from 1 kilometer to 1,000 meters. God bless the metric system. Easy to convert, per 3.5 minutes. So now the speed is in an appropriate unit of measurement in order for us to compare it to this graph. This is a part that I got really stuck on. I could not get the graph to work out. I could not get the equations to work out. And I was racking my brain, and I had to step away from this problem and be like, wait, are my units of measurement the same? And that's when I circled back and was like, oh my gosh, okay, that's what the problem was. So then now I have the speed, and I can represent that in the denominator as 1,000 divided by 3.5. And that's the time on land. If this is a part where you got stuck, feel free to pause the video and see, okay, well, can I figure it out for the sea then? Because now we need to figure out, okay, time spent at sea. So our time spent at sea needs to be our distance at sea divided by the speed at sea. First, to represent the distance, this is not just a horizontal or vertical line, it's at a diagonal, so we need to use our distance formula, which is in your formula packet. And it is the square root of, and you subtract your x values, so we can do x minus 300 squared plus, and then you subtract your y values, 50 minus 0, which is just 50 squared. That is the distance between here and here. Unknown is the x, but hey, notice it's the same unknown as before, so I'm not freaking out too much because we right now still only have one input. So then now the speed. Okay, well, I need to look at my speed of the swimmer. 1 minute per 100 meters. Okay, so the second speed, distance over time, is 100 meters divided by 1 minute. Double checking that my units of measurement are now the same, meters, meters, minutes, minutes, so we can go ahead and keep that consistent across the two different times, which it is, which is good. And it's in meters and our graph is in meters, so everything is working out. Okay, so this is our equation for time. It is a gnarly looking equation, but we can go ahead and it's all in one variable. And let's go ahead and take a look at what this guy looks like on your graph. So let's go ahead and start graphing it. Because I've got a lot of like fractions within fractions, I'm going to hit Control Divide, which then creates this fraction already. So I can just kind of keep track of what's going on. I don't have to be caught up on parentheses. We can zoom standard and then zoom out. With this one, this also took me a while to figure out, is that I needed to hit zoom fit in order for me to really see what was going on. I'm going to zoom out. There we go. So I could tell that I needed to zoom out because my graph had gotten rid of the x-axis. So it had zoomed into some place that was really strange and I no longer had the x-axis. So I needed to zoom out in order to have both of those axes in this sort of way. So I just zoomed out, I zoomed fit so it can like help us figure out the dimensions here. And then zooming out to make sure that we have that x and y axis represented nicely. And hey, we see, okay, there is a minimum. Our time can be minimized, which means I think we're on the right track here. If we're trying to minimize our time, we can find the derivative and find the x-intercept. We can also just use the minimum function in our calculator. But since this is a unit about calculus, why don't we just go crazy here and use calculus? Very hard to see, but we know our x-intercept must be somewhere within here. So I'm going to go ahead and find that. Graph the red one. Lower bound, upper bound. It went ahead and found it. Really hard to see, so I can click and drag. And we can see that our x-intercept happens at 281. Which, hey, is 200 something, but C is not in the appropriate place, right? C at 281 should be over here. So just realize that C was representing the idea of this point that's on the x-axis, but since you didn't know exactly where that point is, you can't assume that that is actually where the point is on the graph. So just be very careful about that. So it just says, where should point C be located? And we know, oh, well, X must be the value where C is located. And we know the Y value because we knew the situation in which this needed to be. And so C must be located at 281, 0 in order to minimize time. Follow-up question, what is the minimum time? Well, we can go back to our original graph and trace and figure out what is my Y value when X is 281. And that is 1.52. This is in minutes because of the units of measurement that we established here from our speed. So we can say 100 or 1.52 minutes. If we wanted to say it in seconds, we can multiply by 60, which is 91.2.